Hello all. So, today we are going to have a discussion on VLSI design subject. This is basically for EC department. So, today this is the first lecture. So, we are going to have a discussion on introduction of VLSI design. In that we are going to discuss about the VLSI design flow, then the integration density and the Moore's law. Okay. So, these are the things we are going to discuss today. So, before proceeding with the VLSI design, we have to first understand what kind of thing we are going to see in this subject. So, as you know that in the VLSI design, the designer has to design a circuit that can give a optimized output, and they most probably want to see how they are having a better performance. Clear. So, from the history point of view, if we see that the VLSI industry reveals the importance of electronic devices, since the invention of your first transistor, that is manufactured in 1947, and that is also called a point contact transistor. So, this has been manufactured in the Bell laboratory by the scientists John Burden, Walter Brattain and William Shockley. So, these three scientists have come up with the first point contact transistor, right. Now, this adoption of BJT completely transformed the electronic industry. Like in the industry, if you talk about the earlier, we are using very heavy devices. So, while implementing all the devices with the help of BJT, we can also reduce the overall area of the device, we can increase the performance of this circuit. So, why we are going for the BJT? Because of it has a more reliability, less noise, and it also consume very less power as compared to the other techniques. So, after that in 1958, the Jack Kilby succeed in integrating the few transistor, means a less number of transistor on a single silicon chip. That also we will see in the upcoming slides, in which I will tell you how they what are the pictorial graph of the integrated circuit, or pictorial representation of integrated circuit. And this functionality of the BJT limits its utilization due to the large leakage current. So, in most of the things, MOSFET, that is metal oxide semiconductor field effect transistor, is became the first priority for VLSI industry. After that, in 1963, the first logic gate was built using a MOSFET technology, in which the CMOS is widely adopted in electronic industry by the VLSI designer due to its ultra low standby power consumption. Means when we are not having any signal to this circuit, even though at that time some of the circuits are consuming power, but the advantage of the adopting the CMOS technology is that it does not consume any power while in the steady state. So, this circuit you can see, this figure you can see that in the first figure A, that shows a point contact transistor that has been manufactured at Bell laboratory, and the second figure that you can see the first integrated transistor, that is only one transistor they have manufactured. Now, we have to first understand what is IC and what are the things inside this IC. So, IC stands for integrated circuit. Now, this IC has three key advantage over digital circuit built by discrete components. So, discrete components means which are having a very lesser number of transistor in a compact IC. So, we can say that it has a smaller size. Second thing, we can say it has high speed. Now, the third point that is very important, that is a low power consumption. Now, the current demand of peoples is always that is having a more energy efficient devices. So, we as a designer, we have some kind of a foundation to create a high performance circuit that can consume a less power with a high speed and within a smaller size. Now, this integrated circuit is now divided into several category based on the number of transistor occupied on a single integrated circuit. So, we have seen that this scale of integration can be small scale integration, it can be medium scale integration, it can be large scale integration, VLSI, that is very large scale integration, or it can be ultra large scale integration or giant scale integration. Clear. So, now you can see that in small scale integration we are having very limited number of transistors. So, the number of transistors can be from starting from 1 to 100 on a single chip, and for example, you can say a logic gates or a flip flop or op amp that can be considered under this small scale integration. Similarly, for a medium scale integration that have a transistor more than 100 and it up to, you can say, it can be up to 1000 transistor on a single chip. And if you take the example of this, you can see 8-bit microprocessor which are having a more number of transistor within the IC, ROM and RAM, that can be 4-bit microprocessor that can be considered as a medium scale integration, and MUX and adder that can be considered as a medium scale integration. Now, if we talk about the large scale integration, we are having an example of 8-bit microprocessor which is having a more transistor in a single chip. It can be between the 1000 to 10,000. Similarly, we are having very large scale integration and ultra large and giant. So, this kind of separation of number of transistor within the IC will tell about whether we are going for a small scale integration, medium scale integration or large scale integration, and so on. So, apart from this, we have to also familiar with the fabrication process, how starting from the fabrication to the testing to the packaging, that also we have to understand how we are going for the high level integration. So, here we are going to start with the I am just giving a brief idea about how these are the things are happening. So, first thing is starting with the silicon wafer. So, we are having a silicon wafer. In that particular silicon wafer, what we are doing, we are based on the application or the requirement, we are fabricating some kind of integrated circuit, some kind of transistors or the components in the particular silicon wafer. Then after that we are making this after making this or fabricating this components in the particular wafer, we are making it to go for the testing. Then the testing process is going on. So, suppose if there is any fault in the particular transistor, then it will be marked and it will be separated out. Once the fabrication is done, after that the testing is done, then after it comes for the packaging. Okay, packaging is also very important. So, we have to go for the packaging, then after packaging again we are going for the testing whether we are having a proper or desired outcome or not, and then the final test of the package will done, then it will go to the market for the as a product. Now, so starting from the journey of this integrated circuit and the number of transistor that has been occupied in a single chip, the Morris has given a law in which they said that after several after having a several observation on the number of transistor that has been occupied on a single IC, they have observed that the number of transistors are getting double in every 18 to 24 months. Okay. And this journey has been started from the Intel processor 4004. So, that also we can see with the help of this diagram, where it is very important to understand how this number of transistors are getting increased with the upcoming years. Okay. So, if we take starting from 1989 to 2026, we can see that the channel length are reducing. So, we have to first understand what is the channel length. Okay. So, channel length is nothing but the channel between the source and the drain, the formation of conducting path between the source and the drain, that we had, that is the channel length. So, as we are increasing, so we are having a different technology node. So, based on the technology node, we can say like 180 nanometer technology node, 90 nanometer technology node, 45 nanometer technology node, 7 nanometer technology node, or currently we are using a 5 nanometer technology node. So, based on the technology node, we can observe that the number of transistor is getting increased. So, in this side you can see that there is a number of transistors, that is getting increased. So, as we increase the year, as we are moving forward to the different years, so the technology node is getting reduced. Okay. So, after that you can see the number of transistors getting increased. So, what are the impact on reducing the technology node and how we have to take care of this impact in the particular integrated circuit, that also we have to look. Now, from here you can see I have just given a pictorial representation of the devices, where you can easily see the size of the device from 0.5 micrometer to 0.3 micrometer. You can see here that the device of 0.5 micrometer is a little bit longer as compared to the 0.35 micrometer. Similarly, if you go for the advanced technology node, advanced technology means lower technology node, that is 0.18 micrometer or 90 nanometer, 65 nanometer, 45 nanometer, 32 nanometer, the dimension of the device is getting reduced. So, as we reduce the dimension of the device, there are several challenges that we have to take care. Now, after that we have to also understand what are the components of the VLSI system, what are the main components that we have to take care while scaling down the technology. So, we are having two things, one is logic functions and the second thing is interconnects. So, in the before 1990s we can say that the importance of interconnect is not that much, because we are only concentrating on the delay of the gate because of low frequency and lower operating or computation devices. But as we are the density of the transistor is getting increased, the more number of interconnect is also required to connect those transistor. So, therefore, we have to take care the importance of both the gate delay and the interconnect delay, both should be taken care. So, in that particular logic blocks we are having functional block, logic gates and the transistor, whereas the interconnect, the use of interconnect we can use to have a power supply or the ground supply throughout the integrated circuit, or through if you want to transport the signals between the blocks of whether it is inter block, whether it is intra block, that also you can do. So, I will show you a kind of pictorial representation of this device and the interconnect. So, you can see that here this is you can say at subtract, and here we are having a different transistor where these interconnects are placed. Okay. So, different level of interconnects are there. So, why these interconnects are required? So, the basic thing is to carry the information from one transistor to another transistor, that is important to transport the signal. So, we have also image for interconnect, the lines that you can see it here, the whatever the lines you can see it here, these all are lines are the wires you can say the interconnects. So, now after that, so the designing process, how one can go for the designing process of any circuit, okay, or any devices, that we have to see. For that, the Gajaski has given a flow kind of thing, flow chart you can say, that is termed as a Y-chart. They have shown how we can divide this process in three category, okay, that we will discuss here. So, you can see it here. Gajaski has given these 3 points and they have divided into 3 domain. One is a behavioral domain, second is a structural domain and the third is geometrical domain. In the behavioral domain, you have to show the behavior of particular IC. That means, suppose someone is one user is having some requirement, he wants some device to get some kind of desired output. So, you have to first as a designer, you have to first have in your hand, you should have some kind of specification in your hand. So, those specification and what kind of output the user required. Okay. So, based on that you have to design your circuitry. Okay. And then we have structural domain, at which particular IC, at what particular components you want to place in what particular area and at what kind of process it should be done. then we are going for the geometrical. So, whatever the outcome you are getting with the particular processor or particular structure, that you have to place somewhere. So, that is come in under geometrical layout. So, we will see one by one. So, we can start with the algorithm. So, that describes the behavior of the target chip, means what are your expectation, what kind of expectation, what kind of output you required. So, that you have particular algorithm, you have to first design the algorithm that can describe the behavior of the target chip, so that it can give a proper output. Then after we are going for the architecture, designing of the architecture of the processor, okay, that we have to define. Then once it is done, once you have defined the architecture of the processor, then it should be mapped onto the chip surface by using either floor planning. Okay, you can use the floor planning to put into the that can be done under the geometrical domain. Now, once it is done, then again you have to move toward the behavioral domain, and you have to give a finite state of machine that is defined for design evaluation, means whatever the things you have designed, now you have to evaluate those designs. Then after that are structurally implemented with the functional block such as register, arithmetic logical unit. Once it is done, then these modules, whatever the module you have designed under the structural domain, then this structure is implemented with the functional block. Okay. Then this geometrical place is now you have designed the functional block. Now, these modules are now geometrically placed onto the chip surface. Okay. So, we are having a chip surface, and this can be implemented there by using a CAD tool or simulation tool, automatic simulation tool that you can use. In that also you have to route some kind of interconnects to reduce the area, to reduce the delay, so that your performance of the IC can enhance. So, in that particular domain you can enhance the performance. So, until unless, and this should be repeated until unless you have a better performance or as per the requirement. Now, in the third, again the module description. Now, whatever the module you have designed at this point, here your module placement is done. Now, what you have to do, you have to go here again in the behavioral domain, and now you have to describe the module. Once the description has been done, once it is described, then you have to go for the logic gates. Now, you have a leaf cells, that can be a chips are described here in the leaf cells, the chips are described in the leaf cells. Now, this cells, whatever the logic gates you have implemented, now the cells placement and routing is used to in the proper location, that can be done only under the geometrical domain. So, these cells, the cells you have designed here in the structural domain, this should be placed in particular chip area. At the last, the details of this Boolean description of leaf cell is defined. Now, and this can be done under the behavioral domain. So, once it is defined, once the it is defined, once you have defined the Boolean equations, then you have to move to the structural domain, and you have to go for the transistor level implementation. So, this can be done by using some kind of software like Synopsys, HSpice, you can do that one, either you can use Cadence Virtuoso, and then once it is done, then you have to go for the mask. Okay. Then finally, mask is generated for the circuit, and now you can go for the fabrication. So, this is another VLSI design flow. What kind of flow we have to follow until we get a desired output. Like I already told you in the previous slide. So, before designing any product or any circuitry, you have some specification. So, first thing you should have a system requirement. First thing is the system requirement, what kind of system you are going to design and what kind of output you expect. So, first your requirement is this thing. So, for that you should have like area, what is the speed, how much power should it consume, this kind of requirement you should have. Okay. and then once it is done, then you are going for the architectural design, means block wise, you are going for the block wise implementation. You will go for the rough sketch of yes, this kind of blocks I can design, so that I will get the proper output. Once it is done, then you are going for the verification. Okay, why we are going for the verification? Because once you go for the verification, then you can observe that whether I am going for the correct output or not. Otherwise you have to again repeat the cycle, and you have to modify your function block based on the requirement. Then you are going for the logic design. So, once the logic design is done, then you are moving further for the verification. Once your expectation is met, you can go for the next stage, otherwise you have to repeat those stage. Then once it is done, then you have to go for the circuit level design. So, once the circuit level design is done by mean of either a Cadence software or Synopsys software, you can again go for the verification. If the requirement is met, then you can go forward, otherwise you have to repeat those things. Then once all these steps are verified, then you are going for the actual layout design. What physical area you have, how much area you are required in that particular area, you have to design your particular layout. Then you are again going for the verification. Once the verification done, then you can move forward, otherwise again you can repeat those particular steps to improve, to optimize your circuitry. Then the actual fabrication is done. Then after that, even after the fabrication, you have to go for the testing, whether after completing all this verification, whether you are getting proper output or not. That also you have to cross check based on the requirement of the user side. Clear? So, if we talk about this implementation, the impact of different VLSI design styles upon the design cycle times and the achievable circuit performance. Actually, we will talk these things in detail in the upcoming lectures, where we can see what kind of methodology, what kind of style we can use to design a particular circuit. Some can take a larger time, some can take a smaller time. Okay, like we are having a semi custom design, we are having a full custom design. Obviously, if you are using a full custom design, then the performance of the circuitry will be much better as compared to semi custom design, but the time required by this full custom will be larger. You can see it here, it takes a larger time, it's having a larger time, but the performance, if you talk about the in terms of performance, the performance is far better as compared to the semi custom. Clear? So, this thing we have to take care. Now, if we talk about the technology, means if we are going from one technology node to another technology node, then also we have to be very careful whether we are adopting a proper technology, whether we are completing those, whether we are implementing those technology in a proper time or not. That also we have to take care. So, the performance is also depend on how fast you are adopting the new technology, whether this technology is adaptable or improvable or not. That also you have to look. So, you can see here for the technology window 1 to technology window 2, here the technology window 1 I am comparing with the technology window 2. So, here you can see it is taking a longer design time for better performance. Obviously, for if you are doing each and if you are creating each and every component by yourself, by mean of giving a large time to implement those circuits, then obviously the performance or optimization process will be done at the backend side, and you can have a better circuitry performance. Whereas, if you are not meeting the proper time, then you can miss the technology. Okay, that means if suppose if one can use a particular area, someone else have designed priorly and you are not meeting, then you are lacking with the current demand of technology. So, you have to take care. So, shorter design cycle times are essential for economic viability. Okay, clear? So, this is all about today's lecture. Hope you have enjoyed this lecture. Thank you.